So let's talk about what is the relationship between points to analysis and alias analysis in terms of expressiveness. Um, so I already told you this is basically what a points to analysis computes, right? But if you look at this interface, so to say, then you will see that it not only talks about variables, but it also talks about these allocation sites. And that may seem very natural, but as I will show you on the next slide, that can actually cause a bit of trouble. Alias analysis, on the other hand, it only talks about variables, right? So we give two variables as an input, and it gives you true or false as an output. And this has some advantages if we have incomplete knowledge about allocation sites, because something you don't know, you cannot really use as a result of your computation. And in realistic settings that we are operating in today with these static analysis, it's entirely plausible that there are allocation sites you don't know about. Let me show you a very simple example program. So let's assume this code that I've highlighted here in this gray box, this read prop method, that is application code. Okay, so it's code that we are actually analyzing of an application, let's say in order to find some vulnerabilities, for instance. And now the analysis encounters this particular method call to properties.read, but read is actually a library method. Okay, it might be part of the Java runtime library. And for instance, for efficiency or scalability reasons, you have decided that you are excluding that library from your static analysis. So that means the static analysis, it will not be able to resolve this read call. It will not know what the body of read looks like, what this method actually does. Okay, it could also be a native method. That would be another reason for why it might be not analyzable for the static analysis. So that's a relatively realistic setting. But now let's assume we want to do some alias analysis, for instance. Okay, and so we might ask the question, can S and default actually alias? Okay, and if you assume that this returns an object, then this is entirely plausible, right? Because if this returns an object, it's being assigned to S, right? Then also you have some aliasing going on here between S and default. So that's the case. May alias of S and default will certainly return true. Okay. So that's actually the result that you want, right? But you cannot simply use the points to reduction that I showed you earlier to arrive at this kind of result, because let's assume what this would do. So if you ask this question, then you first would have to compute the points to set of S and the points to set of default. And this now leads into trouble, right? Because the points to set of default, we can probably still distinguish by looking at the different calling contexts in which this read prop method is being called. But S is being assigned the return value of read, and we don't know read, right? At least that's our assumption. In particular, we don't know whether read at all allocates any object. You know, it could be returning null. And if it does allocate an object, we don't know what kind of object it is, what type it has, or, you know, let alone where it has been allocated. And we don't have any allocation site, right? And so, therefore, what most pointer analysis will return here, and also what Spark would return you in this case, is actually an empty points to set. And that is a problem, right? Because if you have an empty points to set, that's not very helpful, right? So empty would give you an unsound result, right? It would tell you that S and default can never alias, although that's actually definitely the case, right? You might have thought of a different design of Spark, right? So, I mean, as designers or implementers of Spark, they could have used a more conservative approach where this kind of method call, when the analysis processes it, returns a different representation, right? It would not just return nothing, but it would rather return some sentinel object that resembles any object. But this would then actually also be horribly precise, right? Imprecise, because well, if you talk about any object, then basically anything would be aliased with everything else, right? And that's also not a very satisfying answer. And so whenever you have these situations, points to analysis, it has its problems, and therefore sometimes it could, yeah, not be the preferable solution. So just to restate the general problem, so points to analysis associates variables with allocation sites, right? And if allocation sites are unknown, then this association is necessarily either unsound or imprecise, depending on the analysis design, okay? But in comparison, and that's the point that I want to make, alias analysis can recover precision by analyzing the relationship between variables without caring which objects they point to. Okay, so if I take a step back to the previous slide, I could do an alias analysis that works differently. It basically looks just at which assignment statements exist in the program. And in this program, we see an assignment statement between S and default, and therefore we have a relationship between these two variables, and therefore we could make the assumption, the very plausible assumption, that S and default may be aliased at some point in the program. Okay, that's what I'm saying. So even without looking at allocation sites at all, you might use an alias analysis in such a way. Nonetheless, there are cases where you do want to prefer a points to analysis over an alias analysis. And in particular, we already saw when we were talking about call graph construction that points to analysis can be used to actually de-virtualize method calls, right? So if we say this is allocation site A1 here, and we have this call to clear, then I showed you that normally, because this is a collection and there are many types of collections, we don't really know where this clear method call goes, right? So which method is being invoked. But now what you can do using a points to analysis is the following. You can simply compute the points to set of this variable L when you get to this call here. And you will see that it actually contains the allocation site A1. And out of that allocation site, you can then extract the type, right? So you will get the type of this. You can do this for all the allocation sites actually. And then you get a list of types or a set of types like you see here. And you will see that actually this call therefore can only go to linked list.clear, right? To nothing else. And that is a determination that requires the allocation site, right? So therefore, a pure alias analysis couldn't give you that. You really need to take a look at the allocation site and its type in order to infer what this method call will actually resolve to. Okay, so alias analysis it's basically of no use here, right? Okay, that's all I wanted to say about the relationship between points to analysis and alias analysis. I hope that has become clear now. I've also already hinted at this distinction between may and must alias analysis. And there's a notion that is very much related to this, in particular to the must alias analysis problem. And this is the notion of so-called weak and strong updates. So what is this all about? So-called weak updates are generally required if you only have may alias information available. And a weak update is basically an update that one of your flow functions in your flow-sensitive data flow analysis applies to an alias variable. And so in this case, if you do a weak update, it means the following, that for aliases of the variable that you are currently looking at the current statement, information before this statement is retained. So it cannot be deleted. It must not be deleted. That would be unsound. Only new information is added. Okay, so you can never kill information. You can never delete information. Let me show you an example of this. So assume we have a certain client analysis. So that's when I say client analysis, it always means It's an analysis that is using a pointer analysis or an alias analysis in particular under the hood. Okay, so we have a particular client analysis, and in this case, it's a field-sensitive constant propagation. So we want to distinguish different fields, different owner objects of these fields, and we want to determine constant values of numeric variables. And we also assume that explicitly or that everything is initialized to 0. Okay, so at the beginning we have such a mapping here. Okay, and now assume that we only know the following. By our off-the-shelf alias analysis, may alias analysis, we know that X and Y may alias before this statement. Okay, so what does this tell us? So we definitely know that we are updating the field F of the object pointed to by X. Okay, so after the assignment, the mapping x.f to 0 definitely has to be updated to x.f, well, points to 3, right? But how are things for y, right? So y.f might be updated, right? So if they actually do indeed alias, if they actually really do point to the same object, then yes, x.f also needs to be updated to 3, but this may not be the case, right? It might be the case that actually these two variables are pointing to different objects because we only know that they may alias. And you have to account for that second case as well. And that's why using a weak update, you will get the following information. So on the directly accessed pointer that you have here, you do your regular update, right? So this is definitely always being updated to 3, right? But with aliases now, we also do the update, but in addition for this alias variable y and the field access y.f, we also retain its previous state, okay? Because we don't know for sure whether it has been updated or not. And this kind of update where you retain all the old information for alias pointers, that is called a weak update, okay? So that's the whole point about it. So why is this necessary? So like I said, the problem is that, you know, if we only know may alias xy, it tells us that there is a path along which x and y do alias, but there also may be a path along which they don't, right? And so the value of y.f that we store in our abstract representation, that must represent both possible truths at the same time, right? So all the different paths have to be covered. And that's why both of these mappings have to be included. Now let us contrast this with a strong update, okay? Again, very similar situation to what we had before, same statement, same initial environment or mapping that we have here, but now we have a different assumption. Now we have the assumption that we know through a must alias analysis that at this program statement, x and y must alias. So they definitely must point to the same memory location. And then by the same reasoning now, we can do a strong update, right? So we not only know that x.f definitely has been updated to 3, but we also know that definitely the same holds for y.f. And therefore, this previous value here, although it was referring to only an aliased expression, right? So this is not referring to x.f, it's referring to the aliased expression y.f. Nonetheless, because we have this must alias result, we can discard that result because we know for sure it has been updated by this right here, right? And that is called a strong update. And looking at this, you can see why strong updates are nice, right? Because they allow you to always continue to talk about the same number with the same precision, you know, of access paths or field access expressions, or in the very general case, variables and pointers. So your abstract representation, it basically doesn't grow. Whereas with weak updates, we saw it's quite to the contrary, right? So we can always add information, and sometimes we have to add information in order to be sound, but we can never discard anything. And that's not nice, right? So the whole point is here that we can safely kill this outdated value to the strong update. And that's also, again, true in the general case and not only for alias analysis or in this case here, like I showed you in this constant propagation. So no matter which client analysis you use with an underlying alias analysis, you can never kill information soundly on aliases without must alias information. That's why in many cases where you want to have a precise and compact representation of your analysis state during analysis time, must alias information is actually really important. And if you have understood this now, this might seem obvious to you, but if you look 7-8 years back, must alias analysis was really the exception, not at all the norm. So only in recent years, we and others have actually developed must alias analysis algorithms that are precise and also scalable enough to use on real world programs so that we can now actually conduct these analyses properly. There's one further topic that I will talk about in the next break, after the next break, and that is representing aliases with so-called access paths. We've already seen a little bit of this when I was talking about these field access expressions, but there's a general, more general model of this that is also very useful. Yeah, you will learn more in the next video.